Welcome everybody to today's webinar offered by the NanoCommons and NanoSolvit projects jointly with the Nano Safety Cluster Working Group A on Education, Training and Communication. This is Martin Himli speaking from the University of Salzburg. I'm the chair of this working group. I'm also responsible for training efforts in the NanoCommons project. We are having here today with us Marvin Martens and Amar from the University of Maastricht from the group of Egon Willighagen in the Netherlands. And they are going to give us an insight into linked data on the basis of the WikiPathway and the AOP-Wiki and how user interfaces can provide semantic queries and post semantic queries there to facilitate an in-depth search facilities. So we are going to have a presentation of Amar starting actually, and also from Marvin in the beginning, and then we are going to get some hands-on experience into the tool. So they're gonna demo us the links that you can guide us through a couple of queries into the WikiPathways and AOP-Wiki. And I guess, from the presenters, invited to anytime ask questions, and we, the hosts and organizers, will also have an eye on the chat box to post the questions whenever they come into your mind. Let me go through a couple of things. I would like to announce also a couple of useful links with relevance to the content of today. We have in our NanoCommons infrastructure platform, we have several ways how you can get further information on the topic of AOP, for example, because we have had already training events on that. We are we are at the moment actually compiling a user guidance handbook at our NanoCommons infrastructure, where things are kind of fitting together, things are compiled. I will show you just in a second our infrastructure, which make a screenshot if you like from this internet address, which you can access there. And here you are invited to go to the two events, basically the Nano Safety Cluster Education Day Session 1, which was entirely on AOP and things like that. And also there is a Nevada event, which is listed there, the Smart Nano Talks Final Conference, where lots of AOP information was also given. We are also present at the Elixir TESS, and here there are also events, training events and training materials accessible via this link. We are having all our materials at Zenodo, so the slide sets are usually put there, while the recorded sessions go to the YouTube channel of NanoCommons or the Nano Safety Cluster, or both. And I would also like to invite you to join the mailing list of our Working Group A on Education, Training and Communication of the Nano Safety Cluster, accessible via the Nano Safety Cluster homepage, to stay tuned with our training programs if you're not already on the mailing list. So just a short look into this user guidance handbook, which is in development, I have to say. So we are having categories of different interests, and there you would find compiled access to the recorded sessions and the Zenodo linked slide sets and other further information materials. This is a screenshot from our events homepage, and I was mentioning, so this is, for example, the event today. We are going to upload all the training materials, also the recording will be linked there. I mentioned the European Nano Safety Cluster Education Day. This is here the training day. And to have a short look on this, what you see in the Education Day, there is lots of information about what the day was. Also, the entire program is there. And the Session 1, which I have mentioned, you find here in this resources and training materials link, direct access to the recorded sessions. And this was Session 1, which was on this topic where also Marvin gave a talk. The second event mentioned was the Smart Nano Talks International Online Conference, which is also an event mentioned there in our resources. And here you have a direct link also to the YouTube channel where the recorded sessions are posted. Okay, what else? As I said, on the tests of Elixir, we are also having access to our resources. Here, this is the event of today, and also the other ones are listed here. And finally, Zenodo, if you go for the community of the Nano Safety Cluster, or you go for the community of NanoCommons, you would also find access to the information material regarding the content of today, and of course also the session from today. Here, one short glimpse into the YouTube channel of the Nano Safety Cluster. Again, session 1, which we had on AOPs. Okay, well, so with this, I'm thanking you all for being here today. I'm very glad that I can announce now Amar from the University of Maastricht to present on AOP, Wiki, and WikiPathways. So please, Amar, you can share your screen.
Thank you. So hello, everyone. I hope you're seeing my screen now. Thank you, Martin, for introducing us. So I will give you this webinar along with Marvin Martins. We are both PhD candidates at the Department of Bioinformatics at Maastricht University. And the topic of this webinar will be about the online SPARQL access to WikiPathways and AOP-Wiki. I will go more into the details about these two databases or data sources, and talking about how can we use the semantic web technologies to facilitate the usage of and extracting information from these data sources. So at the beginning of this webinar, I will be talking about linked data. So what is it about? What is the point of it? And after that, we will talk briefly about the semantic web technologies lying on top of that, and how the life sciences actually are adapting and exploiting these technologies to gain more insights into the life sciences domain. Second, after that, I will give, both of us will give introduction about two resources specifically where Maastricht University are involved in, which are the WikiPathways and the AOP-Wiki database. And third, Marvin will give you talk about the SPARQL user interface, which is a web application for the SPARQL exploration. After that, I will give a brief description of the SPARQL query language, which will pave the way to the demonstration where each of us will talk about one of those two datasets. And at the end, Marvin will wrap up the session and give a takeaway message and taking your questions. So linked data is a concept has been coined by Tim Berners-Lee in 2006, and the point of it, the idea behind linked data is to move from a web of linked documents to web of linked data. So as you know, the web now is composed of websites, and every website is accessible through a URL, and every page is linked through these URLs with each other. So it's a web of linked documents. And the point of linked data is we go more granularly on this data. So we have each piece of information identified by its own resource, by its own URL, and all these pieces are linked together. So we have linked data instead of linked documents. So linked data is a set of design principles. It's like targeted for two sides, for two things. The first one is to share data. And in order to share data, as I said, you need to have this data reachable through the internet. So you have to give it an identifier, a URL where you can access these pieces of information. And the second side is about machine readable data. So this data should be able to be consumed by software agents that can interpret it and make use of it. And the value proposition of adopting the linked data vision is integrating the heterogeneous knowledge on the internet. We know on the internet there is many formats like images, videos, semi-structured data, CSV and TSV, and websites, and so on. By adopting a unified data representation format, we can integrate this vast knowledge, and we can open the door to find new knowledge inside of this collective corpus of information. The second value proposition is to increase data quality. By using semantic web technologies, we can filter this data, we can apply data quality checks on top of it, which will be very hard to do it with unstructured data like web pages. The third thing is this data will be available for both humans and machines have their own advantages of speed and their accuracy in doing some specific tasks that we can utilize the machines to do when we have our data in this format. And the last one is to enable data analysis techniques and the whole emerging fields under data science to analyze this data and make more use of it. So on top of linked data, so linked data is a set of design principles. On top of that, we have a set of tools and technologies. It's called semantic web technologies, and those are the technical side of linked data that allows representing and querying this data. Specifically, among semantic web technologies, we have RDF and SPARQL. So in this slide, I will show you in the left what are those technologies are to distinguish between these concepts. So on the left, we have the query language, SPARQL. It's actually a language. It's simple, sort of. It's not like a full programming language. It's just a query language that allowed you to devise questions where you can ask these questions against a certain database and get information back from it. The second, in the center, the second part, we have the data representation and the data model. We use for that a technology called RDF. It's an acronym for Resource Description Framework. It's a simple principle of representing data. As you see under the logo, we represent every piece of information as what we call a triple. The triple is composed of 3 parts: the subject, the predicate, and the object. So we always encode our data as triples. So for example, the subject could be a gene, the predicate could be participates in, it's a verb or participates in, and the object could be a pathway. So gene X participate in a pathway or involved in a pathway. This is a piece of information. It could be, for example, a disease is related to a pathway. So every piece of information, we encode it as a triple. And these triples, naturally, when you create a lot of them and you use a specific encoding of these entities, they will be linked together, and we will have here a form of a graph or a network where each entity is linked to many other entities in the graph using those the predicates that we define. So for example, in this simple graph, we see Bob. Bob is the subject here. He is interested in is a predicate, and the Mona Lisa is the object. So this is one triple. From the other side, Bob is also a subject, but is a friend of, this is another predicate, and Alice is the object. So Bob is a friend with Alice. This is another triple, and so on. This is how the data looks like inside our data and our data set, and this model technique is called RDF. After that, so we have now the data representation, we have the query language, and we want to put this data somewhere. And traditionally, we have databases, relational databases to store our data sets. I'm sure many of you are already familiar with this concept of relational databases. But here, since we have this different data structure that's called a graph or triples, we want somewhere to store them. And for that, triple stores were made. A triple store, it's a data store for graph data. And there is many vendors for such programs. Probably you would recognize some of them, like BlazeGraph, GraphDB, and Virtuoso. And those are some of the options of triple stores to store graph data. To make this more we can align this model with the traditional relational databases, I will show you here the query language, for example, SQL. This can be compared to SPARQL for semantic web technologies. Instead of RDF in relational databases, we have the entity relational model where the table is the focus in the ERD model. And also instead of triple stores, we have relational databases, servers like Oracle, MySQL, and SQL Server. So this is how the semantic web technologies stack aligns to the relational databases stack. In life sciences domain, many areas has adopted the linked data approach, and with all the semantic web technology stack. And as we see in this you will have access to the slides, and each one of these logos, if you click on it, it will take you to the corresponding RDF or SPARQL endpoint where you have access to this resource. So here we can see many big players in the field of life sciences like PubChem, Campbell, BioPortal, and also for pathway information, WikiPathways, Cake, and NanoCommons, UniProt for proteins. All of those already have their data encoded in RDF format, and they provide also interfaces to communicate and query this data using SPARQL language. Our focus here today is on two data sets specifically from the previous data I showed, and those are the WikiPathways and AOP-Wiki. I will start introducing the WikiPathways, and Marvin after that will take the lead to talk about the AOP-Wiki database. So WikiPathways is a community resource to contribute and maintain biological knowledge in the form of pathways. You know that the organisms involve a lot of complex interactions, and that takes a form of pathway for metabolic processes, signal transduction, regulatory processes, and other types. So pathways is a way of representing this knowledge in a way that is visually understandable and comprehensible by the humans. So WikiPathways was an initiative to collect and curate from literature and by volunteers from the community this kind of knowledge, and also this resource support a variety of ways to integrate and interact with the pathway content. So there is image maps, there is RSS feeds, and the REST APIs to communicate with the WikiPathways to ask certain information about the content of those pathways, and for example linked references to them and their content like genes, proteins, and metabolites. On top of that, WikiPathways supports and adopts the linked data approach. So all the content of WikiPathways is available as RDF, and we also have a SPARQL endpoint where you can query the content of WikiPathways using SPARQL language. So now I will go to Marvin so he can talk to you about the AOP-Wiki, and then we continue our webinar. Marvin?
Yes, thank you, Amar. So the Adverse Outcome Pathway Wiki, AOP-Wiki, is a part of the AOP knowledge base and is developed by the European Commission's Joint Research Center and US EPA, Environmental Protection Agency. And it stores adverse outcome pathways, as the name implies. These are defined as a framework that captures mechanistic information or knowledge on toxicological processes, and it supports making decisions in risk assessments. It basically forms the bridge between toxicological knowledge or toxicological data and the knowledge-based regulatory risk assessment. You can see an adverse outcome pathway as a chain of biological events that start at the molecular perturbation by a stressor, which can be a chemical or a nanomaterial, which causes a chain reaction in the shape of other biological responses, leading to an adverse effect, often on organ or individual level defects, such as organ failure. The database, we have worked on this database and transformed it into RDF as well, and we have made it available through a SPARQL endpoint, and we will, after this demo, the SNORKEL user interface that we created on top of that. Okay, next slide, please. So the SNORKEL user interface is a user interface that makes the exploration of SPARQL databases much easier and much more convenient, and provides a couple of functionalities to make it more user-friendly for everyone. As you see on the right side of this screen, there's the two screenshots of the SPARQL or SNORKEL user interfaces of WikiPathways on the top and AOP-Wiki on the bottom. They are fairly similar, but they have been adapted visually to fit with the theme. The new functionalities that SNORKL user interface has on top of the regular Virtuoso SPARQL endpoints that we have is that they have a SPARQL editor with syntax highlighting, which I will show in a minute as well. It has a query panel on the right side, which is loading SPARQL queries from a remote GitHub repository and can be used in a very flexible way that will also be demoed. It also allows for a couple of exports to different file formats and has a full screen and an option, a full screen option and the option for sharing queries through permanent links, which makes it very easy to send particular SPARQL queries or results of them to others through the web. Okay, next slide, please. So first, the SPARQL editor, the SPARQL query panel. Can you click one more time? It provides highlighting of your SPARQL query, which makes it much more easier to first understand what's written in the ones that are loaded in there, but also it makes it easier to write them. You can see that variables are a blue color. The really systematic parts of SPARQL are in purple. Comments are in orangey yellow color, and literals are in red, which makes it easier to read in respect to creating the SPARQL query and using it. Next slide, please. The next section is about the example panel, which is on the right side of the user interface. And the first bit of that on the top, you can see there's a URL to a GitHub repository. That's where you define which SPARQL queries are being loaded in the bottom there, where you see all the folders. Can you go to the next slide? So this is an example of the SPARQL query repository of WikiPathways, where it's very simple folder structure where you have a organization which you can do in any way you want. And it has subfolders where you can enter folders and you can see the queries in there. They are created with a .rq extension. Next, click please. And these queries that are loaded in this SPARQL or in this GitHub repository, they are loaded in the very same format as it is in this GitHub repository. Next slide, please. Another click. Yes. So this makes it very convenient to browse through different SPARQL queries inside of these folders, also within subfolders of these, and really organize all of the questions that you might want to ask to the database. At the third box that is in the right side, there's also a search option. So if you have a particular interest in chemical or in a particular entity that you're looking for, you can also really quickly search for SPARQL queries that have that in their name. Okay, next slide, please. The last bit is the additional buttons that were created in this user interface, which is really about the exports in various formats. Now it's CSV, in JSON, and in XML. But also there's a full screen option, which makes the SPARQL editor full screen, as it says, and it gives you a lot of space for writing your SPARQL queries, and as these can get quite large. And there's also the permalink option, where you get a pop-up on the screen, you get a URL, and this URL, you can share this one with everyone, and when they click it, they have the exact same query that you have on the screen at that moment. Next slide, please. And that's back to Amar.
Okay, thank you, Marvin. So now after we've seen the SNORQL interface, which actually facilitates the way you interact with the queries and how do you organize them and export the results of them. I will give a brief explanation about the SPARQL query language, a small example of how does it look like. Since this presentation or a webinar is not meant to give a technical guide on how to use SPARQL and RDF and so on, it's for disseminating the set of tools we have on top of that. So we will, in the demo, we will show you fairly simple queries, and of course, depending on the level of your experience with that or the knowledge you will be acquiring later, you can extend those queries and write your own more complex queries. So the SPARQL query structures, if any one of you is familiar with SQL, the structured query language for relational databases, it's very, very similar to it. It was intentional to make it similar to ease the like moving from the relational databases to semantic web databases or semantic resources. So in this example, the query is composed of mainly several sections. The first part is a select part. A select is a reserved keyword for the SPARQL, and here you define which variables you want to extract from the knowledge base to view in the final table. This is correspond to the column names in the tables in SQL, for example. The where, of course, you can also use comments by using the hash character. After that, you document your query or whatever description you want to provide. The where keyword is where you specify the conditions that on which you will based on you will get the variables from the output, and the conditions here are in the form of triples, as we've seen before: subject, predicate, object, and each line is terminated with a dot, signaling the end of the triple. The last part of the query, it's optional, so you can use order by keyword to order the results. For example, maybe it's a date, or it's a number, or it's a string value, so you can order the results. There's other keywords in the SPARQL query language, like a grouping. If you want to group a certain variable by another variable, you can also use that. It's a bit bigger than this, but this is a simplified version of a SPARQL query. So when you will see the demo, it will not be very strange what is this query means and so on. So now I will move to the demonstration. I will start with WikiPathway's SNORQL interface, and we will go through a couple of queries and see how can we make use of the RDF version of WikiPathways. Okay, so this is the SNORQL interface for WikiPathways. As Marvin indicated, this is the SPARQL query editor, and here is the examples panel, which actually you provide the GitHub repository link and will automatically grab every RQ file in that repository and preserve the document structure, so you can put your queries on GitHub and you can just use them here using the GitHub API. So here for WikiPathways, we already have quite some queries that are targeted at different areas of interests, depending on your specialty or your domain. If we started with the metadata part, it's mainly about information that describe what's inside the WikiPathway database. For example, the counts of the pathways, the count of genes. I'm going to give an example here. If we went to the species folder, and then we can have, for example, the pathways for specific species, the count of data nodes per species, the count of genes products per species, and also the metabolites, the pathways, and so on. If we choose the count of pathways per species, automatically the query will be grabbed from GitHub from the corresponding file name. It will be pasted here. If you want to modify it, you can modify it here. You see this is editable area. If not, you can just hit the query button. The query button will send this SPARQL query to the triple store, will ask about this information encoded as RDF, as I showed you before, and it will bring back the results in form of a table. So if you see here in the select part, we are asking for 3 pieces of information: the name, the organism, and the count of the pathways. And then we are seeing this information, the name, organism, and the pathway count. So if we see here all the species that have pathways in WikiPathways, we have quite some of them. Homo sapiens, humans have 1,180 pathways related to them. For others, like the mouse and the rat and so on, have less numbers, but WikiPathways has really good coverage of organisms, and especially focused on humans. The next query I'm going to talk about, so for example, here, if you want to go to the communities where we put queries that are of interest to certain group of people. So people want to know something about COVID-19, there are queries related to that. AOP, adverse outcome pathways, they can go to it. Lipids and lipids map, rare diseases, and so on. I'm going to pick an example from the lipids folder, and we have here a query called lipids count per pathway. So for example, this query uses comments extensively, so it documents every line in the query to tell you what does it do. Here also we are asking about the pathway and the title of the pathway and the count of the lipids in that pathway. As you see here, there is a condition in the where part in this line. It filters the pathway on a specific species. In this case, it's Homo sapiens. So if we hit the query button, you will see in the results the URL of the pathway, the ID of it, the title, and how many lipids are mentioned in that pathway. The nice thing about this SPARQL interface, it's connected to the WikiPathways actual database. So if we click on the URL of the pathway, you will see the actual pathway, and you can navigate and explore it more. But at the same time, you can get informative information about it, for example, like the lipid counts in here. There is an easy way, for example, to adapt this query. If you remember, we looked here about the count of pathways per species. I will do this query again. Here we have the names of the species available in WikiPathways. For example, if I copied the mouse one and I went back to the lipids query, you can just change the Homo sapiens here and put the mouse one and do query again. And here you will have all the pathways that are related to the mouse, and you will see the number of lipids in each one of them. So this is, SPARQL is very extensible, and it's easy to use once you get the grasp of the main building blocks of it. I will move, for example, to a third example. This one will be from the general folder, and it will be about the genes of a pathway. So in a similar way, this query will show us each pathway, and you specify one pathway here in the filter, and it will show you all the genes related to that pathway. So for example, this pathway that has the ID WP1560, it will give us this list of all the gene products inside this pathway. Those are the symbols for the genes, and then you can also open that pathway from this link here, and you will see all these genes will be mentioned here, like this one, for example. And then you can, using the WikiPathways website, you can click on a gene and you can get external references to it. So the other ID for that gene, this is the HGNC symbol. Here you can get the ensemble gene ID, the interest gene ID, the gene ontology annotation of that gene, and so on. So you see the integration between the actual WikiPathways image maps here, and how the SPARQL can give us more information about it. So the fourth example I will go to is the metabolites of a per pathway. It's similar to the gene one. If you look, I'm clicking difference between them. The only difference is instead of filtering on a gene product, here in the metabolites, it will be about a metabolite product. You can still specify the pathway that you want to filter the results on. You click query, and then you will see for the same pathway that we filtered on for the genes, we will have now a list of metabolites. So we see calcium, CGMP and the DAG and so on. The last example I'm going to give, and I think this is could be also important, if you are looking you found a pathway, for example, in WikiPathways, and you want to know where pathway is coming from, the interactions in it, where they are coming from, you would like to have references. So this is the query here. It's called all pathways with a PubMed reference. If you click on it, we'll wait a second, because this will search in the whole WikiPathways database. It will bring us for every pathway the corresponding PubMed references mentioned in it. And I will show you in a bit an example of how can we filter on a specific pathway. So here, for example, the pathway and the PubMed URL that reference that pathway. If we open that, this will give us the publication where the pathway or part of it were extracted from. I will show you one final query here, but we will make use of this feature of changing the examples repository. I have another repository here different from the one currently. You just copy the URL of the repository of yours and you paste it here, and you hit on the refresh button. You will see here the content are different. So now we have two folders, metabolomics and miscellaneous, and those are actually coming from the GitHub repository. If you open the metabolomics one, you will see those queries inside, and the same here. If you opened it here, you will see the same queries already grabbed from GitHub. This is the query that I wanted to show you. It's similar to the one that already executed here, but instead of listing the whole PubMed references for all the pathways, this is maybe not very informative. This query adds a filter here that show you only the PubMed references for a certain pathway. So if we hit the query again, we will see that this pathway has already two PubMed references linked to it. This is the first one, and this is the second one. And this could be very important when you want to do citations. If you are looking for certain interactions and you want to find where this is coming from, you can use the SPARQL interface to do this kind of filtering. Whenever, for example, if you changed this identifier to something else, to another, for example, this is a random one, and you want to save this query for later use, or you want to share it with others, you can just use the get permalink. Here you will get a permanent link that you can just send it to others. When they open it, they will get exactly the same query as when you generated that link. So this is an easy and convenient way for sharing the queries, especially if you modify them in the query editor, so they will be preserved for sharing and later use. I will go back to Marvin now, so he will go with you through the AOP-Wiki SNORKEL interface. Marvin?
Yes, thank you. So indeed, this is the SNORKEL interface for AOP-Wiki. And specifically for this webinar, I created a GitHub repository which has the demo queries. So if you can go to the query panel there, just add -demo behind it and then hit refresh. And it will open all of the queries that are in the newly created GitHub repository. I put them in order so it's easy for you to go one by one. So the top one is one of the simplest queries, but a very useful one. Is just exporting all of the adverse outcome pathways that are captured inside of the AOP-Wiki. It's really simple. It defines the variable that is a adverse outcome pathway, and it asks for the title, the name. This is a very simple example of how you can really quickly get a lot of content from the AOP-Wiki, create a full overview of what's all in there. In terms of adverse outcome pathways. And of course, all the links that are also in these are clickable and you get to the pages in the AOP-Wiki normally. So go back, you can go to the next query. The same we can do for key events, which are the smaller building blocks of adverse outcome pathways. And this query, if you execute it, it will return to you all of the key events and all of the key event titles of all of the key events that are in the AOP-Wiki. Things that we can do here is also filtering. For example, I have one commented line in there on line 6. If you remove that, it will filter the key event names on all of the mitochondrial key events, which gets you back a whole list of all of the key events which have the name mitochondrial in their title, which is quite a lot of them. Since the mitochondrial inhibition or disruption is often part of many different adverse outcome pathways. Okay, next query, please. So this query, it will get you all of the chemical identifiers that are mapped to the various stressor chemicals that are in the AOP-Wiki. This was an addition that we had placed to allow for the interaction with more databases and have just identifiers for many different chemical databases connected to the stressors that are captured in the AOP-Wiki, which makes it more easier to identify which chemicals are actually being talked about or described in the AOP-Wiki, to link it to data or to make connections to other databases. And I will show an example in the last query later. Next query, please. The same exercise we did for the protein ontology annotations that are part of the key events in the key event components section, where protein ontologies we mapped to all of the identifiers from NCBI and from other databases to have really the gene identifiers that are part of these biological objects, which are the central components of many key events, especially at the molecular initiating event level. So this makes it very nice that you can identify which exact gene or protein is the subject of particular key events. Okay, next one. Another example here is querying of a particular adverse outcome pathway of interest. In this case, we filter for adverse outcome pathway 38, which is the protein alkylation leading to liver fibrosis. And this is extracting all of the key events that are part of this adverse outcome pathway and all of the methods that are described in these key events to measure or validate the occurrence of these key events. And this makes it very easy to make an overview of all of the measurement methods in a particular adverse outcome pathway, which you saw, like this is only a millisecond work, and you get all of the table as an output there, and you can really quickly share this and export this in any way. You have all of the content nicely organized. Okay, next one. So this is another query that looks for all of the molecular initiating events and all of the adverse outcomes that are in some way related to the key event 117, which is the most used mitochondrial dysfunction key event. It's part of many adverse outcome pathways, and therefore it has many connections both upstream and downstream. So many molecular initiating events can lead to this mitochondrial dysfunction, and many adverse outcomes can result of the mitochondrial dysfunction. And this really quickly gets you an overview of all of these connections that are available in the AOP-Wiki. And there's, as you see in the query results, in the SPARQL results on the top, it says 26 results. And that's the count of how many of these combinations of molecular initiating events and adverse outcomes it shows. Okay, next one. This one is a bit the same, but it is making it much larger. This actually gets you all of the key event relationships of all adverse outcome pathways that have this particular key event of interest. It is still the same key event of mitochondrial dysfunction 1. And this is really getting you back all of the relationships that have something to do with this key event. So you can basically build a whole network out of this. You have all of the nodes and all of the edges directly into this table, which are all surrounding this one particular key event of interest. So this is really an efficient way of getting all of this kind of information, which would take you a lot of time if you would do this on the wiki itself. The next one is the final example, but a more complex example where I look at all of the adverse outcomes, which are about fibrosis. So if you see line 12, it looks for all of the fibrosis adverse outcomes. It returns you with in total 3 different adverse outcomes that have fibrosis in their name, 3 different ones. But all of them, I also ask for which adverse outcome pathway they are a part of, which also gets you all of the links that all of these adverse outcomes are a part of. And it gets also the chemicals, the stressors that can initiate these adverse outcome pathways. So it really gets you from the chemical level. In this case, I request the Cas identifier and gets you back all of the adverse outcomes on, gets you back all of the adverse outcome pathways that have to do with fibrosis. Okay, and the last query is a nice example of how to combine different databases with each other. So this is a so-called federated SPARQL query, which starts in the AOP-Wiki, where it searches for chemical identifiers, in particular CABI, from the CABI database. It looks for the adverse outcome pathways that these are a part of. And then it uses a service call to go into the SPARQL endpoint of WikiPathways. And there, with the same CABI identifier that we identified in the AOP-Wiki query, we can look for all of the pathways, all of the molecular pathways in WikiPathways that this chemical is a part of. So with this, we can really make the connection between the adverse outcome pathways in WikiPathways, which describe chemical interactions, and molecular pathways that are present in WikiPathways. And if you see here, there's on the left side the chemical and the adverse outcome pathway columns, and on the right side we have the molecular pathways of WikiPathways, and they are all stored next to each other. And this gets you, this is showing the power of what this kind of linked data can do. This is just 2 databases that are linked to each other, and within a few seconds you can really create a big data set of information that is not possible in any other way to create, and that is really something very valuable. This thing is also very flexible, so you can request any type of information from both of these databases and make even more additional service calls after that if you're interested in more information from other databases that have SPARQL endpoints or RDF. Okay, that's my demo. Then the last bit is really about the small summary, the take-home messages of this webinar. We have talked about the technologies, RDF and SPARQL, and why they are useful in the life sciences. We see that many databases already use this kind of technologies. And we have shown also with the demos that it's really a powerful tool of exploring data, exploring RDF data with SPARQL queries. And as seen in the last example, linking databases. And this is just one example of, I would say, an unlimited amount of examples you can try for making connections between various databases. Also, we have shown the new functionalities that the Snorkel user interface creates with the basically a user interface as a SPARQL workspace, we can call it. It makes it easier to create queries, to reuse queries, and just have a whole panel of examples available right from the beginning. It has a flexible, adaptable layout, as was seen with the interchangeable query panels with the GitHub repositories. And it has a functionality of really quickly sharing SPARQL queries with each other instead of having to copy and paste and store the whole SPARQL query at an external location. It is just in the form of a short URL. Okay, and with that, I would like to thank you. This was the end of this webinar. If there's any questions left, or if you have any suggestions for us, I'm happy to hear them or answer the questions. And I hope Amar as well.
Yes, sure. Thank you, Marvin.
Thank you very much, Marvin. Thank you very much, Amar, for this great insight into your work and into this obviously quite useful linking methods. The floor is open for discussion. So discussion, comments from the audience.
We have one question in using the question function in the control panel. Is there any part of this program where one can simulate and see these stress effects happening?
I guess that's about the adverse outcome pathway information to see the stress events happening. I don't exactly know how to answer that question. I mean, all of the information that is in the AOP-Wiki, it includes evidence of molecular interactions, also with regards to the chemicals that are described there. So if that information is captured in the AOP-Wiki, it is also retrievable through this user interface, because this has everything that's in there. But maybe I misunderstood that question. Is this about validating, or?
If you would like to elaborate on your question, I can unmute you so you can tell us. You'll have to unmute yourself as well.
Okay, thank you. Good afternoon. Oh, nice presentation. What I'm actually asking is, in the program itself, is there like any graphical demo that's not only on just a coded programmable language level, where, for instance, you have some of these nanotoxicological effects on human organs, just to see probably if there might be some interactions on real time. You simulate and you see maybe these kind of attacks with oxygen species, or maybe it's attacking the lungs or attacking the mitochondria without just, I mean, coding. I know you spoke about user interface. Yes, that's the program is on a coded level. So what I mean is just like simulate, and then you see like if you code and then you query and you see what you queried, perhaps you can also, I mean, simulate to see on real time what is actually going on.
Yeah, I think I understand what you mean. Like you want to use this in different environments. Do you want to like combine this with kind of modeling or simulations?
Maybe yes, simulations, because user-based, while you code and then you can see what is happening, like on a background, or maybe how these effects are being manipulated and how they are being how they are just happening. That's just the only question I am asking. But it's well, I understood the lectures of the presentation. So I was just wondering, maybe there could be something like that also in this pathway.
Yeah, these tools are very easy to integrate in risk assessment workflows or just computational workflows. So like Jupyter Notebooks, for example, where you can execute SPARQL queries from the coding environments and really get the answer directly, and use this for other kind of questions or databases or tools or modelings. It is a possibility, but these things are not a part of the AOP-Wiki itself.
Marvin, maybe one question along this road is, since we are now linking these two quite big data resources, how big actually are they? So how many entries does AOP-Wiki and WikiPathways in this? One of your example was linking these. What are you then kind of querying? What kind of volumes?
Yeah, you can count the data in triples, I guess. So for example, if we would, I'm now in the same time I'm executing a SPARQL query, select all triples. And in the AOP-Wiki, we would get to around 122,000 triple entries, which is subject, predicate, object, as Amar described in the beginning. In the WikiPathways, it's much larger though. This one has a lot more information, and I'm now copy pasting the exact same query there, which gets us to 18,821,000 triples. So this is a very large amount of data. In terms of size, like in megabytes, the AOP-Wiki is quite small. It's in between 10 and 20 megabytes in size, the RDF file. For WikiPathways, it's over a gigabyte.
Okay. This somehow visualize how powerful it is. Another question that I had in my mind is, in what way are you cataloging the queries of which you were showing a couple of examples today?
Are you answering, Armand?
Yeah, you mean how are we creating these folders? Like on what basis?
Yeah, or how many of these folders are there? How does one access them if one doesn't know already
No,
where to
actually,
look it up?
if you open the URL of WikiPathways or AOP-Wiki, you will see immediately here the GitHub URL. So if you can immediately copy that link and go to GitHub, and you will see how many. This is the second one that I already showed, but you can see how many folders we already have, and you can already use these queries automatically by default when you open the program. But you can also, as we said, create your own queries, and then you use the URL for your GitHub repository to show them here. And the SNORQL interface will memorize that URL for you, so you don't have to enter it every time. So yeah. And actually, this list of queries and these groupings of queries is evolving through time. So at the beginning, we had a couple of them, and then whenever a certain community is interested in queries, and through our collaborations, like for rare diseases, lipid maps, COVID-19, we keep enlarging and extending this repository with new queries. So there is no limit, and it's not like limited to the current folder structure. It could be extended, and the queries are increasing every now and then. I hope that answers your question.
Yeah, thank you. Okay.
Sure, welcome.
We have a few more questions from the audience.
Sure.
We have lots of AOPs listed in the AOP-Wiki are underdeveloped. What happens when those AOPs are updated?
Sorry, can you repeat the second bit of the question? I had some noise on the background.
Okay, sorry. So what happens when AOPs are updated?
So the RDF here, it's based on the exports that the AOP-Wiki provides. It provides permanent downloads every 3 months. And also the RDF, this SPARQL endpoint, is updated in the same schema. So it uses the quarterly downloads. So the next one will be the 1st of April. And this will be directly uploaded here in this user interface, or in this SPARQL endpoint that this user interface uses. Yeah. So every 3 months it will be updated.
Okay, we've got a few more questions coming in. So is the AOP-Wiki updated with relevant information on adverse outcome pathways on nanomaterials? Yeah, there's quite some initiatives in developing adverse outcome pathways for nanomaterials, or at least apply adverse outcome pathways in the world of nanosafety. These are, although they are a lot harder to get out of the database, since these are not really annotated with identifiers, or they have no clear way of identifying these. And it's often text written how these are implemented in there. I had a few other SPARQL queries where I really look at these nano-specific stressors and nano-specific key events. So they do exist, but there's no good way of really extracting only these yet. Considering nanomaterials, how can you differentiate between a nanomaterial or a chemical by using all the chemicals function for the AOP-Wiki. Not sure I quite got that.
That relates to the previous one. That is a
Yeah.
tricky one. We have tried in the past to work with the CABI ontology, since CABI does, on top of its identifiers for chemicals, it also uses an ontology for describing what the functions are, what the relationships to other chemicals are, and really in a hierarchy of functions. And there's nano material in there. But so far, in that method, we haven't found anything yet, unfortunately.
Okay. And then there's another one. Can a query be made to identify OECD validated AOPs, or which stage they are in development?
Yeah, there is definitely, it's a variable inside of the AOP-Wiki. It has a statement of OECD status and various other statuses. And these are also extracted. These you can also extract through this SPARQL endpoint and filter on them.
Okay, that's the last of the questions that people have put into the question function. Martin, was there anything you wanted to add?
I also do not see anything. I just wanted to thank Marvin and Amar for this excellent presentation and hands-on insight into how it's functioning. Please bear in mind, we are going to provide this material online by means of all the different sources that I have mentioned in the beginning, the NanoCommons infrastructure, the handbook, Elixir tests, the recordings at our YouTube channel of NanoCommons Nano Safety Cluster. Stay tuned with us. We are going to have, in less than a month, again, a training session, which we are going to announce by all the different channels that we have. Okay, so thanks everybody for joining. And if there are no more questions, I would then close the webinar for today. Thanks for joining, thanks for coming, thanks for presenting. Thanks for hosting, Lee.